Okay, now I think we can start. So let me introduce myself. I'm Godfrey Odhiambo. I'm a physics mathematics teacher in Kenya, Kunda Secondary School. I'm also a PhET fellow. So tonight I'm going to take you through a teaching with PhET, and I'll zero in the pedagogy. So I welcome you all so that we can share together through this one session, and I believe it will be fruitful. Now, I'll start with PhET interactive simulations. So PhET is a suite of research-based interactive computer simulations for teaching and learning physics, chemistry, mathematics, and earth science. Now, in Kenya, earth science is geography. So the simulations are able to demonstrate and transform abstract concepts into interactive visual content, and hence support active and collaborative learning. So the simulations also allow interaction between students and the simulated equipment. Simulations provide students with feedback that allows them improve their knowledge and skills. Simulations also allow for role-playing and hands-on learning. Therefore, at the end of the day, the simulations improve students' learning. And that is according to Rutten, Van Degen, and Van der Ven in 2012. So a teacher and students can utilize simulations in the following ways. So number one, to provide homework. Number two, you can also use the simulations in a class activity. You can use the simulation as a virtual lab. The simulations can also be used as a resource for the teacher and the student. So the teacher can also use the simulations in demonstration in class, and also during remediation or advancement by the learner. So the goals of the teacher when they're using simulations are as indicated. So the first one is visualizing the content that the teacher is teaching. Then the next one is a conceptual understanding, so that the student can understand the concept being taught. The next one is an exploration, so the student explore. Then the student will discover knowledge. The student will inquire and enjoy, and also make science teaching to be very interesting. The student also will use simulations to build connections with real-life scenarios, and also the student will gain so much in implementation and scientific reasoning when maybe they interact and discuss in class. So the students will also gain in collection of data, collaboration, calculations during class work, and maybe assignments, verification of data or laws and principles, and also the student will gain in following instruction and proceed in concept that he or she is learning. So the sessions also help the teacher to design experiments to be used by the learner. So the characteristics of passive learning environment and active learning environment as enumerated. So the first one, the teacher and maybe the textbook are the qualities and resource of knowledge. The students' beliefs are rarely overtly charged. The students may not challenge their belief. So if they believe on something that is not correct, they will have it to the end. The students may never even recognize differences between their beliefs and what they are told in class. The instructor or the teacher is an authority. Now, on the other hand, in active learning environment, students construct their knowledge from hands-on observation and manipulation of a simulation. The students are challenged to compare predictions based on their beliefs, and they compare with the observable real experiments done in the laboratory using the physical equipments. Active learning environment also changes students' beliefs when students are confronted by differences between the observations and their beliefs. So the teacher's role is a guide in the learning process, and those are the characteristics of an active learning environment versus passive learning environment. So a continuation is that in a passive learning environment, the lectures often present the facts of science with little reference to experiment. So the teacher will teach, there's no experiment done. Then laboratory work is, if any, is used to confirm theories learned in a class. And this one in Kenyan schools mostly do it because we think the time is limited. So collaboration between peers often discouraged. So there's no pair and share. While in an active learning environment, the results from real experiments are observed in understandable ways, often in real time, with the support of microcomputer-based tools like simulations, and in this case, PhET sims. So the laboratory work is used to learn basic concepts in science. So the student is involved. So there's a collaboration and sharing learning with the peers. Now, in a teacher, when the teacher is using the simulations, so before the start of the activity, the teacher is encouraged to give the students about 5 minutes for an open play. So the open play helps students to familiarize themselves with sim environment, so that by the time the main activity is taking place, the students will have known how to manipulate, how to click any icons provided in the sim. So the teacher is also encouraged to pause for about 2 or more times for the activities. Like the first one is open-ended questions, which are called challenge prompts, where the students are given the challenge prompts, and a characteristic of a challenge prompt is that it has various correct answers. So the challenge prompts also help students to cooperate and also interact in a group environment. So the teacher also asks the students to discuss their thoughts on a question with someone sitting next to them. So they think and share in a class. Now, in Kenyan schools, because of a lack of resources, we have certain types of teaching pedagogies that help in the classroom. So these types of teaching pedagogies are called whole class strategies, and mostly they are used when the laboratory is not well equipped, and maybe the teacher has no time, or the number of students is enormous, like maybe 60, 40, and the quality is limited. So therefore, to encourage it so the teacher can use whole class strategies. So the first is a whole class inquiry. So the teacher designs a guide, that is the design questions to guide the discussion, and the questions are ordered in a coherent way during the development of the lesson. So it is the teacher who manipulates the sim according to students' suggestions and answer to questions. So the teacher allows students to describe what is happening in the sim. Now, in this case, the students are not given an opportunity to manipulate simulation. So therefore, the students may not be, maybe the amount of knowledge, maybe the amount of content learned may be limited. So an example that I've decided to give out in physics, because I'm a physics teacher, and this one can be replicated to other science subjects and mathematics. So example is this. So there's a topic in physics called electrostatics, where we use a capacitor. We use a capacitor to teach physics. So the question is, what effect on the capacity will occur when the plate area is increased? So the student is given two choices. The first one, reduced. The second one, increased. So the students will suggest the correct answer. And after that, the teacher will manipulate the sim. So this is an example of the sim environment itself, where on one side the area is 100, on the other side the area is 400. Then the student will compare the area. So the first one, the area is smaller, the next one, the area is larger. Then the plate charge is given there. The capacitance is 0.09 times 10 negative 12 farads. In the other side, right side, the area is 400, that is bigger. The capacitance is 0.35 times 10 per negative 12 farads. So the student is able to determine which one will give a higher capacitance. The next question, which is question 2, what change will occur on the capacitance when the distance operation is increased or reduced? So in this situation, the lesson is developing, and the students will give their suggestions, of which the teacher will confirm using a sim. So this environment, we are looking at the distance of separation. And in this case, in the left part, the distance is increased, that is 10.0 millimeters. In the right part, the distance is reduced, and that is 5.0 millimeters. So the students will be able to observe and check which one exactly will make the capacitance will increase and which one will make the capacitance reduce. Now to the left, when the distance is 10 millimeters, the capacitance is 0.09 times 10 power negative 12 farads. To the right, when the distance is 5 millimeters, the capacitance is 0.18 times 10 power negative 12 farads. So at that point, the student can differentiate which one is the correct one and give out the correct suggestions at the end of that part. The third question is what effect do introducing a dielectric have on the capacitance of a parallel plate capacitor? So what effect does it have on the parallel plate capacitor? So on the left, there is no dielectric between the plates, and the capacitance is given as 0.09 times 10 power negative 12. On the right, there is a dielectric between the plates, and the capacitance 0.44 times 10 power negative 12 farads. So the student is able to use the sim to have some knowledge in it. The next one, question 4, what change will occur on the capacitance when the area of overlap between the dielectric and the plates is increased and or reduced? So this question, after the students have given their suggestions and given explanation to why they have chosen the answer, then the teacher will now demonstrate to the students using the simulation. as shown in that slide. So in the first case, the area of overlap is smaller. The capacitance is 0.14 times 10 power negative 12. In the middle part, the area of overlap is greater than the first part, and the capacitance is 0.28 times 10 power negative 12 farads. On the right side, the capacitance is the area of overlap is a maximum. Not even the area, the area of overlap is maximum. So therefore, the capacitance is 0.44 times 10 power negative 12 farads. So the student is able to differentiate between the three scenarios. And according to the slide given, the area is increasing from left to right and reducing from right to left. So number 5, what effect does increasing the dielectric constant have on the capacitance and or the energy stored? So the teacher will ask such a question, then the students will give their answers, of which the teacher will confirm using the sim. So in the left side, the dielectric is at minimum, increasing the electric K. On the right side, so on the left side, the electric is 1. On the right side, the electric is 5, that is increasing. And the capacitance on the left side is 0.09 times 10 power negative 12. On the right side is 0.44. So the student is able to differentiate between the two and have some knowledge at the end of that part. So in this situation, the student is not given permission or an opportunity to use the simulation. So the next strategy that is used to teach, the next strategy used is interactive lecture demonstration. Interactive lecture demonstration. Now, in this method, it is designed to enhance conceptual learning in large and small math and science classes through active engagement of students in the learning process. This pedagogy is more student-centered than the whole class inquiry method. That's the first one we've looked at. So in this situation, it gives the students some chance to engage or interact with the simulation. Now, the students engages with activities that confront their prior understanding of a concept. Also, it introduces a carefully scripted activity, that is the predict an outcome. So the students will predict an outcome, and in the next slide, we look at that. So the prediction part, the students are led to predict the outcome of a demonstration individually. Then in pairs, the students explain to each other which set of a possible outcome is likely to occur. So during the experiment part, where it's either the students will do it or the teacher will do it during the demonstration. So in small groups of about 3 students, they conduct an experiment, they take a survey or work with the data collected to determine whether their initial beliefs were confirmed or not. Now, in this situation, the students have an opportunity to interact with the simulation where they will confirm their belief and either disapprove what they have learned and learn again. Now, the reflection part, that is after the demonstration, the students will think about why they held the initial beliefs and in what way the demonstration has confirmed or contradicted their beliefs. So students learn to learn and or learn to unlearn and then learn again. So in this situation, the students will learn to learn, that is, they'll confirm their belief. and or they learn to unlearn, that is, they remove the initial belief they had, which was not correct, and then learn the new belief, which now is correct according to the SIM. So the ILD is done in this way. So the teacher identifies a core concept that students will learn. The teacher will choose a demonstration that will illustrate the core concept. Then the teacher will prepare written materials that can easily follow the prediction, experience, and reflection. And that is, these documents are the lesson plan, activity sheet, and reflection sheet. So an example of interactive lecture demonstration is as shown. So the first demonstration, so there's a sketch, there's a question there given to the students. So the student is asked to sketch below your prediction on a graph of capacitance against the plate area of a parallel plate capacitor. So the students will give a prediction. They will share in groups of 3, and then they will present their prediction. So there's a follow-up question which the teacher will also ask. Example is describe the effect of doubling the plate area on the capacitance. The next one is a sketch below your prediction, a graph of capacitance against distance separation between the plates of a parallel plate capacitor. So even this one is a prediction which the student will predict and discuss in groups. Then the teacher will do the demonstration, or the students will do demonstrations in a group, and they will confirm their earlier belief. So the teacher will do a follow-up question as given in the example. Describe the effect of doubling the distance between the plates on the capacitance. So this is an example of a question that the teacher will use. Number 3, sketch below your prediction on a graph of capacitance against the electric constant K. So the student will predict, they'll share, then the teacher will demonstrate, or the student will demonstrate using the SIM, then a reflection will occur. The follow-up question will be described using a material with a high electric constant on the capacitance. So that is now the follow-up question that the teacher will give out. Demonstration number 4, sketch below your prediction on a graph of energy stored by the parallel plate capacitor against the electric constant K. So in this scenario also, the students will give a prediction. They will share their prediction in groups, discuss their prediction, if it is correct or not. Then either the teacher or the students will do a demonstration on the SIM and give a reflection. So the follow-up question, an example, will be given as describe the effect of using a material with a higher electric constant on the energy stored by the capacitor. After the predictions, then the teacher goes through the various parts of the simulation according to the activity sheet. So there will be an activity sheet that will be given to the students, and also the teacher will go through it. The students in groups will interact with the simulation according to the instructions given in the activity sheet. So the next part, which is the last part, will be the concept questions. Now, concept questions also are referred as concept checking questions or CCQs. So questions which are designed to check learners' understanding. So these questions provide a good complement to conventional numerical problems because they need minimal or no calculations. So in this scenario, a student who has a problem with calculations will have a benefit. So the questions encourage students to engage more deeply with the underlying concept which is being learned at that time. So an example of a concept question that is learned in physics is which of the following is correct? Now, for concept questions, the teacher will come up with distractors in form of multiple choice, which the students will commit. Then they will take a vote. After the vote, then now the demonstration will occur. So which of the following is correct? So the first one is increase in plate area increases capacitance. The next one is increase in plate area increases total energy stored. But C, increase in plate area increases potential difference across the plates. Now in this scenario, we have the teacher will put a diagram so that it can help the student determine which one is correct. After that, then, so after that, the students will carry out, or the teacher will do a demonstration the way that one is happening there with a sim. So after that, the students will have a look at capacitance and the plate charge, the stored energy using the sim, and confirm if the initial answer given was correct or wrong. The next question is which of the following is correct when the distance of separation between the plates is increased? So the first one is capacitance increased. The second one is energy stored increased. The third one is potential difference reduces. Now, in this case, the students will also commit to an answer, take a vote in either groups or as a class, and the teacher or the students will do a demonstration individually or in groups. So example of a demonstration is that one, where the teacher is doing the demonstration and the student is monitoring or checking, observing what is happening in the sim environment. Number 3, so the question number 3, which is a concept question, is introducing and electing the plates. Number 1, increases energy stored and reduces the capacitance, or increases both capacitance and total energy stored, or reduces capacitance and increases the plate charge, or but D, increases the voltage and across the plates. Now in this scenario, the students will also commit to an answer. They'll take a vote, and the teacher will do a demonstration, or the students will do a demonstration either in groups or individually, depending on availability of a computer or a phone or any resource. So the demonstration looks like that. So we have that demonstration, capacitance increasing as the electric is being introduced. So we have that, so the students will observe the way it's happening there. Now, during the activity, the teacher moves around the classroom to answer questions and interact with students to learn more about how they are thinking. Also, the teacher will communicate with the students and also try to maybe help or intervene in situations where the students are stuck. Now, the interactions will confirm the ways of which the teacher will do a follow-up, or a clarification and highlight the students' ideas. So after the activity, the teacher should offer a timely and constructive feedback to students after the activity, either in large classes or in small classes. So the teacher will also explain both the correct and the incorrect answers, which some students will have guessed. It is important so that the students can now learn to unlearn the previous concept which was incorrectly learned, and also try to get the correct one at that moment. So the teacher is required to be clear about how the activities and the outcomes of the activities the students have undertaken make the connection with the goals that are learned in class. So the teacher must construct explanations and design solutions by, one, summarizing relationships between variables that the students observed using the sim, explaining why the systems behave the way they do based on the observations from the simulation. So the teacher uses the simulation as evidence while doing the explanations. So also the teacher will design solutions based on evidence from the sims. So the teacher should engage in arguments from evidence by, one, justifying conclusions using observations and data collected from the simulations, and discussing the simulations and how they implicate or the implications in the real world. That is connecting what is learned in class with what is happening in the real world scenario. So up to that point, the references to this information I've given out are as shown in that slide. So I will give out this recording so that the teachers can engage with it and reflect, and maybe also learn how to use the sim in class. So any question or any concern, you are now free to ask. Welcome, all of you. And thank you so much for coming in to this call. So you can just unmute yourself and ask any question that you may have. Yes.
Godfrey. Hey, Godfrey, are you getting me?
Yeah, I'm getting you.
Okay, my question is,
Yes.
how you can get the simulations offline? That was something you had explained before this meeting.
Yeah.
Yes, I was just asking how you can get those simulations offline on your desktop, that is.
Now, I want to share with you
a
link of the offline simulation. Or instead of sharing with you, I think I should go to the website itself. Yeah, let me share the website itself and how to access that simulation offline. Let me share the website. Let me check this website to be shared here. Yeah. Okay, I've got it. So is my site visible? So the website is a PhET. Let me go into the website. Now from here, you can go down, down from the website. Then there is this. Are you seeing it? Offline access. You click this one. Then it will come to this Windows app. You download Windows app on a Windows. Download Windows app, this one, or you download a Mac OS if you have a Mac laptop. So you can either use this one or this one. So I encourage you to use this for Windows, this one for Mac. Got it?
Yeah. Thank you. Thank you so much.
Thank you so much. So anybody has a question? Any other question? You are free to unmute and ask. We have about 12 minutes to go. You are free to unmute and ask any question.
Yes, Mr. Godfrey, can you post the link on the chat section?
Okay. Let me do that now.
Thank you.
Let me check where the link is. So I've shared. Have you seen it? So the links there will contain anything that we require, and it will help a long way in you accessing the SIM and also using the teacher tips that are provided in the website. So any other question? Yeah, so in conclusion, I'm grateful that you've joined me in this call, and try so much to use the offline SIM. So download the offline SIM. The offline version will help so that when you are in an area where the internet is low, you can access the SIM and utilize it well. So any concern, any problem trying to access the simulation, you are free to contact me either through my email or my phone number. I'm always available at your call. So thank you so much, and welcome. I appreciate the time you've taken to join me in this call, and it's not taken for granted. So thanks a lot. So maybe if anybody has a question, a concern, which can be addressed before we close, you are free to do so. So you are free to take your leave at any time, at any moment from now. Welcome. Thanks a lot.
Okay. Thank you too. Have a good night.
Good night to you.
Thank you.
Thank you so much.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you so much, Mupe.
This was obviously a big obstacle for them. Not only was he not